speak like you don't have a microphone.
Okay.
Really try.
Okay, so this is to pass the slide.
Yeah, we try.
Which one is it? I can use the computer. I can use the arrows. Okay. I will use this. It's okay.
And you can also, if you need to, okay, so just right and left, and then if you need to.
Okay. Hello, everyone. So
wait one second, I'll introduce you.
Sorry.
So our next speaker will be Clémence Chevignard, who will be speaking about new Icart-Type encodings from elliptic curve automorphisms.
Thank you. I will be talking to you about an attempt from Mehdi Tibouchi and I at building new hash functions toward elliptic curve by taking inspiration of the construction of Icart-Type encodings. I will begin by presenting the motivations for this work. Then I will introduce some preliminary notions that are called exceptional covers, and I will also explain how to find some. And finally, I will present the details of the construction of our new hash function. So the first question we can ask ourselves here is, why do we need hash functions toward elliptic curves for? Well, you can see on this slide that there is a lot of cryptographic algorithms that make use of this kind of hash functions. Like, for example, you can think of identity-based encryption schemes like Bonnie-Franklin one. You can think of parent-based signatures like BLS and so on. And maybe seeing all of this, some of you are thinking, okay, there is a simple solution to get the hash functions we need. Suppose that you want to hash toward an elliptic curve E that has a base point P, and that you already have a hash toward the integrals modulo n. You can simply send an element of FQ to the base point P added h of aim time, and this should give you a suitable hash function, right? Well, actually, this is not a very good candidate, because the problem with this construction is that everyone that knows the original hash function h knows the discrete logarithm of the final point. So if we want to use this kind of naive construction with cryptographic algorithms that have their security relying on the discrete logarithm problem, for example, this is very problematic. So this is why we will need to use hash functions that are a little bit more sophisticated. Currently, we distinguish mainly two types of families for hash functions toward elliptic curves. The first one is called SWU-type encodings, and the second one that we will be interested into is called Icart-Type encodings. We can consider that this kind of encoding is structured in the following way. Suppose that, consider the projective line P1, an elliptic curve tilde E that is the curve you want to reach, and another curve C that is not necessarily elliptic. And suppose that you have a rational map pi from C to P1 that is bijective, and a cover from the curve C to tilde E. Then you can consider the encoding H defined as the composition of the cover F and the inverse map of pi. And the interesting thing with this kind of construction is that because the rational map pi is bijective, we can show that the encoding H has a lot of nice properties, and we can use a lot of classical hash functions construction with it, and it will give us something that meets all the classical security requirements for this kind of object. So at least in my opinion, I think this is a very elegant encoding. However, if you look at the original article from Icart, you see that he only gave one family of curves C for each elliptic curve tilde E we could want to reach. So the natural question that arises here is it possible to generalize this, this construction and to use it with maybe different kind of curve C? And this is exactly what we will be trying to do today. And for this, we will consider two steps. The first one is to be able to build curve C that have a bijective rational map toward P1. And the second step is, given the curve C, to find covers toward elliptic curve tilde E. So before explaining in detail how we are going to do that, I need to introduce the concept of exceptional cover. Suppose that you have two curves x and y defined over a finite field fq, and that you have a function f from x to y. We can say that f is an exceptional cover from x to y if it induces a bijection from x to y on every extension of fq that is of degree t coprime to an integer m, a fixed integer m. So by extension, we can also say that a polynomial or a rational function defined over fq is exceptional if it induces a map from P1 to P1 that is an exceptional cover. And unfortunately, this can be a little bit confusing, but an exceptional cover can also be a curve. Namely, we will say that a curve x is an exceptional cover of another curve y if there exists a function from x to y that is an exceptional cover. So there is something important to note here. 2 slides ago, I said that the first step for construction would be to look for curve C that would have a bijective map toward P1. To be more precise, what we will be doing is that we will be looking for curve C that have that are exceptional covers of P1. The difference is that we don't want pi to be bijective only on FQ. We want it to be bijective on infinitely many extensions of FQ. Fortunately for us, we have a very interesting result from Bisson and Tibushi that gives us a methodology to build polynomial and rational functions that are exceptional cover. Namely, if you consider an isogeny phi from an elliptic curve E to another one, that is of prime degree greater than 5, the 3 following conditions are equivalent. So if the X rational map U phi has no FQ rational pole, it also means that there isn't any point of the kernel of phi that has its coordinate in FQ square, and it also means that the X rational map U phi is an exceptional rational function. And fortunately for us, it's not very difficult to find isogeny phi that meets this requirement. For example, you can consider an elliptic curve E that has no m torsion points over FQ square, and consider any isogeny of degree m, and it will give you something suitable for this result. So here we have a pretty easy way to build polynomials and rational functions that are exceptional covers, but what we want is a curve that is an exceptional cover of P1. So to do that, we will need another result from Fried, that is the following. If you consider any polynomial G defined over FQ and U phi that is an exceptional rational function, the curve C defined by this equation is itself an exceptional cover of P1 if you consider the projection on the y coordinate. So this result combined with the previous one gives us a useful way to build exceptional covers of P1. In the following slide, we will mainly consider one polynomial g that is y squared, and we will consider this kind of curve C with a small change of variable. Please note that we can always, in our setup, decompose the expressional map u phi as the quotient of a polynomial u by the square of another polynomial v. Okay, so we managed to complete the first step of our encoding construction. Now we wish to be able to find covers from the curve C to elliptic curves TLD. Actually, this is not a very easy thing to do, because, I mean, we could think about listing every kind of exceptional covers C we can find with isogenies, and then trying to see which elliptic curve we can reach from them, but this would more or less consist in building a database of pairs C and TLE that works with this construction, and this is very impractical if we want to use this construction for a real-life application. What we need precisely is parameterized equations for the curve C, the curve F, and the curve TLE, so that we can choose the parameter accordingly, depending on which elliptic curve we want to reach. So we tried several approaches to do that, and there is one that leads to surprisingly simple expressions for the cover F and the final elliptic curve TLE that I'm going to present. So the setup is the following. Consider that we work in a finite field FQ that contains a cube root of unity omega, a non-trivial cube root of unity, and that we are working with original elliptic curve EB defined with this equation, so that the elliptic curve EB has an automorphism of degree 3 defined by the root omega. In this case, we know what the endomorphism ring of EB will look like, and so we know it's isomorphic to the quadratic ring Z of omega, and this allows us to know that the curve EB will always have two endomorphisms of degree 7 that are defined like this, and that will commute with the action of the automorphism of order 3. And actually, because those two endomorphisms commute with this automorphism, we know that they will have a quite particular structure that is detailed right here. So actually, we can consider the curve C defined by the expressional map of those two degree 7 endomorphisms. And we can also consider the cover F defined by this equation right here, that will go from the curve C to an elliptic curve TLE that has this equation. And you can see that the equations defining F and TLE are pretty convenient. Furthermore, it's possible to explicit the expression of the two degree 7 endomorphisms. So in the rational field, we get this kind of expressions for u phi 1 and u phi 2, and this tells us that we are able to reach the following elliptic curve TLE1 and TLE2 with those two endomorphisms. And here, at first sight, it seems that the equation defining TLE1 and TLE2 are depending on the coefficient b that allowed us to define the original curve EB. Okay, so maybe you are thinking, cool, we can choose any value for b we would want to, and we can reach any kind of elliptic curve we want. Well, actually, it's not that simple. If you look a little bit closely at what we just did, you can see that the original elliptic curve EB always has the same G invariant, that is 0. And remember that we want the degree 7 endomorphisms phi1 and phi2 to define exceptional covers of P1. So this happens actually only if those two quantities are not a cube in the finite field FQ. So this leaves us with 2/3 of the possible choices for the coefficient B that are suitable for what we want to do. And finally, if you compute the G invariant of the two final curves tilde E1 and tilde E2, you see that we have the two following formulas that are completely independent of the coefficient B. So actually, what we are able to do here is that we can hash toward two possible G invariants for each Q, and for each of these G invariants, we can reach 4 isomorphism classes of curves. So now that we have our encoding defined, the first question we can ask ourselves is it secured enough? Well, I won't go too much into the details of the security of this construction because, because our construction is structured in the same way as Icart-1 is, we can use exactly the same kind of argument to show that the final encoding H that we get is well distributed and strongly well distributed, which means that we can use any typical construction of hash functions with it. So if you want a concrete example, consider two hash functions H1 and H2 and the final construction described right here when we send an element mu to the encoding of H1 of u plus the encoding of H2 of mu. We can show that if H1 and H2 are independent random oracle over FQ, then the final hash function we have with this construction will be indifferentiable from a random oracle toward tilde E. The second question we need to ask ourselves is, okay, we have our construction ready, but how are we going to compute it concretely? I mean, given an input y, how are we going to compute the final point p associated to y? Well, if you look at the structure of our construction, you can see that we can once again distinguish two steps to do this. The first one is to find the point of the curve C that is that corresponds to the input y, and this is equivalent to finding a root of the polynomial right here. And the second step is, once we have the curve of the point of the curve C associated to the input y, to compute to evaluate the cover F on the point of the curve C. The second step is straightforward. If you remember the equation we have for F, it's really easy to do so. So the difficult part here is the first step. A naive way to do this would be to use an algorithm such as Cantor-Zassenhaus 1, for example, to just find the root corresponding to the input y. But this would not be a very wise strategy, because we want our encoding to, we want to be able to compute our encoding in constant times, and this is very this is not easy to do that if we want to use probabilistic algorithms such as Cantor-Zassenhaus 1, for example. So actually, we know that the rational function u phi is exceptional. So this allows us to know that we can solve it by radicals. And moreover, we have a very useful article from Fagal and Lazare that gives us a guideline to express explicitly the root of this polynomial. So this is actually not too difficult to do. Okay, so to conclude this presentation, we distinguished two steps to build hash functions based on Icart methodology. The first one is to be able to build curves that are exceptional covers of P1. And we do that from isogenies of elliptic curves. And the second step is to find covers from such curves C to elliptic curve tilde E. So far with this method, we are able to build two encodings toward two gene variants of elliptic curves for each value of Q we could use. And we know that our encoding has the same security level as Icart-1, and we also know that we can evaluate it in constant times. But of course, for real-life application, being able to reach only two gene variants for each characteristic we could want to use is not very practical. So it seems necessary to explore other approaches with this methodology, and this is a work in progress. Thank you very much for your attention. If you have questions, go ahead. If not, no problem.
All right, let's thank our speakers. Okay, so that was a very nice talk. So would anybody like to ask a question? The audience here, and do we have any questions on Zoom? Are there any questions on Zoom? Okay, I'm curious if you could say a couple more words about the about reaching other J invariants. What sort of obstruction and what sort of new tool might be needed?
To reach a more elliptic curve, you mean?
Yeah.
Currently the main strategy we are exploring is, how do I explain it? We have a theorem in Prolegomena to a middle bound that gives us a simple criteria to know if a genus 2 curve can be can have covers to elliptic curves. It consists in looking in the factorization of the degree 5 term in the equation defining the genus 2 curve, and we are trying to see if we can build this kind of genus 2 curves with degree 5 exceptional degree 5 isogenies that gives us exceptional rational map, and then to factorize them and express the cover explicitly, which is time consuming, unfortunately, because we have to express roots for this, and well, it's a little bit complicated, but currently that's what we're trying to do to reach our goal.
Great, thank you. Let's thank our speaker again.
Thank you.